This is the screencast for section 8.4, example 8. We're going to test for convergence and divergence. Now, don't get too excited. This isn't exactly as efficient as it seems. I don't really see myself testing for convergence or divergence before I actually find the area under a curve, but a test exists and it's good to know how that works. So here we go. Theorem 6, the comparison test. Basically, if you have the antiderivative from a constant to infinity of a function, that will converge if the area under a curve from that same constant to infinity of a different function converges, as long as that other function is the bigger of the two values. It's kind of like sandwich theorem in a way, because if your f of x function is between 0 and the other function, it'll have to converge if the bigger one converges. And same thing with diverging. And that would imply that if the bigger function diverges, the smaller one will also diverge. Alright, so let's investigate. Does the integral from 1 to infinity of e to the negative x squared dx converge? Well, I don't know, but I do know that e to the negative x squared is always going to be greater than 0. And e to the negative x, so without the square, is always going to be bigger than e to the negative x squared. So that means that the antiderivative, or area under the curve from 1 to infinity of e to the negative x squared dx, is also going to be between 0 and the antiderivative from 1 to infinity of e to the negative x dx. So if I test to see whether this function converges or diverges, I'll be able to see whether e to the negative x squared will. So I'm going to take the limit as b approaches infinity of the antiderivative from 1 to b of e to the negative x dx. See what I mean? You're still doing the same process, it's just with a different function. So it's not really efficient, it just works. So the limit as b approaches infinity of negative e to the negative x of 1 to b would have to use fundamental theorem, and then I get 0 plus 1 over e, which is a constant, of 1 over e to be specific. Therefore, the antiderivative from 1 to infinity of e to the negative x squared dx does in fact converge. Now, this whole process didn't tell us what the area under the curve is, but it did tell us that it converged. We found the area under a different curve. So now try problem number 31. Says use the comparison test to determine whether the integral converges or diverges. Well, I know that this function is always going to be greater than 0. And I also know that 1 over e to the x is also going to be greater than this function, because I don't have in the additional 1 in the denominator. That 1 in the denominator is going to make smaller y values because the denominator is greater. Which therefore implies the area under each curve from 1 to infinity is also going to have the same relationship. Well, if I evaluate the bigger of the two curves, so 1 over e to the x from 1 to infinity, that will help me see whether the function at hand converges or diverges. So I'm going to take the limit as b approaches infinity from 1 to b of 1 over e to the x dx. So I'm going to take the antiderivative, which is negative e to the negative x, evaluate from 1 to b, so fundamental theorem part 2. And then I simplify to get, I take the limit to get 0 plus 1 over e, which, look at that, again is 1 over e. Therefore, the antiderivative from 1 to infinity of our function that we were asking for in the first place does converge, just because the bigger function does also converge.